Welcome again as we consider yet another multiple choice question for IB Chemistry. Which complex has the greatest d orbital splitting? So when students look at this question, they immediately notice that it's asking about d orbital splitting, and immediately their thoughts would go to topic 13, the colors of transition metal complexes. In that topic, the students learn that the colors of these complexes depend upon the identity of the transition metal, which is true. The oxidation state of the transition metal, that too is true. The identity of this ligand, which forms a coordinate covalent bond with the central metal ion of the complex, that also is true. In the IB Chemistry data booklet, the spectrochemical series is provided to show which of these ligands cause the greatest splitting in the d orbital system. And that's what the question's asking about. Then you have all of these oxidation states and you have different metals. But all of this data in this question here is actually there as a distractor, because to arrive at the answer to this question, you only need to consider this information here. And you also need to connect this to topic 2/12 of the IB Chemistry Guide, where you learn the visible part of the spectrum is made up of red, orange, yellow, green, blue, indigo, and violet, and that red has the longest wavelength and violet has the shortest wavelength. So wavelength decreases going this way and frequency increases going this way. And this information must be combined with your understanding of how the d orbital system is split. Of course, the d orbital system made up of its 5 parts, split in this way, 2 components elevated above and 3 components down below. Then these transition metal complexes acquire their colors when white light strikes the complex and electrons are excited from this ground state to their excited state. When this happens, certain specific frequency and wavelength of light is absorbed, and what's not absorbed is transmitted. What's transmitted is what we get to see with our eyes. So if you have a big amount of splitting, then the amount of energy between this point and this point is going to be very high. And if the amount of energy is very high, then you need to recall that E equals h, which is Planck's constant, multiplied by nu, the frequency. So which of these colors has the highest frequency? Violet, indigo, blue, they have the highest frequencies. Those colors would be associated with a big level of splitting, but it's when those colors are absorbed that you get the big level of splitting. So if blue and violet and indigo are absorbed, it means you have a big level of splitting. And then what gets transmitted? Here is where you need to bring in some understanding of complementary colors. And you don't need to fully recall the color wheel, but if you can, it's very useful. And a quick way to remember a simple color wheel like the one shown in the IB Chemistry data booklet is to have your 6 components here, to have red, orange, yellow, green, blue, and violet, with indigo kind of like meshed in with violet, between violet and blue. And here you have 400 nanometers, and here you have 700 nanometers for the longest wavelength for red and the shortest wavelength for violet. So you're going this way. So if something is violet, then it's actually violet because it's absorbing yellow. And yellow doesn't have such a high frequency, as you can see. Frequency increases going this way. So with this information, you realize that if something is violet, it means it's absorbing yellow. And yellow is lower frequency. So E equals h nu won't be very high. So if something is green, then it's absorbing red, which again, red is all the way down here, frequency is very low, E equals h nu would be very low. But If something is orange, then it's absorbing blue. Blue is all the way over here with a high frequency. It's going to have the highest value out of all of these. The orange color is going to arise because when the d orbital system is split in B, it absorbs radiation. It absorbs light in the blue part of the spectrum. And what's left is predominantly in the orange part of the spectrum, which is why we see orange. It's because blue is absorbed. And here we see blue because orange is absorbed. And here we see violet because yellow is absorbed. And here we see green because red is absorbed. And all of those have a lower frequency. So when you take that frequency and you multiply it by Planck's constant, you're going to get a lower value for energy. So to solve this question, you needed to bring all of those other topics, and you needed to put this part aside about the identity of the metal, the oxidation state of the metal, and the identity of the ligand. And all of this was here as a distractor, which would waste your time in the exam. So if you immediately focused on this, you would be moving straight to the answer of B.